Welcome to the short video description that shows progression of our re-executed Bayesian adaptive design of the ALLHAT study that accompanies the manuscript by Luce and collaborators. Do Bayesian adaptive trials offer advantages for comparative effectiveness research, virtually re-executing the ALLHAT trial? This project was funded by the NHLBI, and its goal was to demonstrate proof of concept of Bayesian adaptive trials in CER. In our previous paper, published in Clinical Trials in October 2013, we investigated 7 different design variations, incorporating various combinations of adaptive randomization, arm dropping, and early trial stopping for success or futility. Limiting ourselves to the assumptions the ALLHAT investigators used during the design of the actual trial, we compared our various designs' operating characteristics to each other and chose one design we would have executed had all the state-of-the-art clinical trial techniques available to us today been available when ALLHAT was designed in the early 90s. In this paper and in this short video, we'll show how this redesign would have progressed when using the actual ALLHAT data. ALLHAT was a large, very well-conducted clinical trial of over 40,000 patients run in the mid-90s to compare diuretics to 3 relatively new competitors for hypertension. Rather than just seeing how each improved blood pressure, ALLHAT used the more clinically relevant primary endpoint of non-fatal MI and fatal coronary heart disease. ALLHAT was designed to have 82% power to identify a 16% benefit in each arm. So now imagine halfway through the patient accrual, this is actual ALLHAT data, when we have 20,000 patients and over 18,000 patient years of follow-up. We observe the data in the following table shown here. ACE inhibitors are showing very little benefit versus diuretics, a hazard ratio of just 0.98. Calcium channel blockers are showing a 13% benefit, a hazard ratio of 0.87. Good, but still smaller than the 16% benefit the trial was designed to show. And alpha blockers are somewhere in between, a 9% benefit, just over half the effect size the trial was powered for. Of course, this was blinded data, and we didn't get to see it. But if you got to observe it and got to allocate your future resources, namely the next 20,000 patients, how would you do it? There's no right or wrong answer to this question. Maybe you keep going as planned. The confidence intervals for all 3 arms clearly contain values reflecting improvements even beyond a 16% benefit. But maybe you think it really looks like ACE inhibitors aren't any better than diuretics, and combining that with the observed effect size on calcium channel blockers is smaller than the 16% we powered the study for, maybe I'd reallocate some or all of the patients we have planned to go to ACE inhibitors toward calcium channel blockers to ensure we have sufficient power to show if there's a smaller effect size there. We don't have this luxury in clinical trials, and if we did, we wouldn't know what things like our type 1 error probabilities are. But if we prospectively decide what changes we make using prospective decision rules, then make those changes according to the data we observe in the trial, we can still calculate our key operating characteristics like type 1 error and power. That's precisely what we did in reAdapt. I won't go through the decision rules here, they're in the paper, and other rules we explored are in our clinical trials paper. So let's see how the Bayesian adaptive trial we chose to execute progressed. We're going to show you a plot in a table that looks like this at what would be each interim analysis. The top will show the analysis number, the number of patients enrolled, and the time from the first patient randomized. The left shows the Kaplan-Meier curve for each of the 4 arms. The colors of the curves match the colors of the labels on the right. Our first planned interim analysis occurs after 10,000 patients are enrolled and includes a futility analysis in the event that all 3 comparator arms are doing much worse than the diuretic. That wasn't the case, and the trial continued. At each analysis, we see the number of patients randomized to each arm so far under the N column, the observed MI and fatal coronary heart disease rate per 100 patients, along with the estimates of the standard error. Notice that after 10,000 patients are enrolled, the rate is much higher, 2.36 events per 100 patient years for ACE inhibitors versus around 1.33 for calcium channel blockers and alpha blockers, and 1.82 events per 100 patient years for diuretics. The next column shows the number of observed events in the patient years of follow-up on each arm. Then the probability each of the 3 comparator arms has a better or lower event rate than diuretics. Since this is a Bayesian analysis, if a comparator arm had an equal event rate to diuretics, the probability the arm has an event rate less to control would be 1/2. Based on the current data, 10,000 patients, though most with limited follow-up, there's only an 18% chance ACE inhibitors have a better event rate than control, but an 84% chance calcium channel blockers and alpha blockers are better than control. Next, we show the probability each arm is best amongst all 4 arms in the top in each group here. we see there's a 5% chance diuretic truly offers the lowest event rate versus a 1% chance for ACE inhibitors versus 48% for calcium channel blockers and 46% for alpha blockers. The bottom number in each of the three blocks here shows the values when comparators are compared just to one another. A 1% chance ACE inhibitors is the best comparator, while the other two arms are in a virtual tie for which offers the lowest event rate. Finally, using the data available and the decision rules prospectively described in the paper for randomization probabilities, we calculate randomization probabilities for the next round of patients, about 2,500 patients. The randomization rate for diuretics is fixed at 33%. It changes to 0 for ACE inhibitors because those patients are doing so much worse than the other arms. And the remaining probability is about equally split between calcium channel blockers and alpha blockers, since those two arms are performing equally. Importantly, the ACE inhibitor arm is not terminated, and patients who were randomized to ACE inhibitors don't have their treatments changed. And we're just not going to randomize any more patients to ACE inhibitors and instead let the data mature. Now, about 3 months and 2,600 patients later, we perform our next interim analysis. This one for updating just randomization probabilities, not potentially stopping the trial. The ACE inhibitor rate has improved. It's better than diuretic now, but it's still worse than the other two arms. The calcium channel blocker rate is still the same and the best. And so in the next wave, we randomize 33% of patients to diuretic. That's always the same. 34% to calcium channel blockers, and the remaining probability 15% to ACE inhibitors, which is doing the worst, and 18% to alpha blockers, which isn't doing much better. It's important to see what's happening here. Calcium channel blockers seem to be the best treatment, even though the trial is young. And the trial is putting more patients on control and calcium channel blockers in order to increase study power to find a significant difference between control and the best among the three comparator arms. At 15,000 patients, about a year and a half into the study, we see calcium channel blockers are still in the lead, and alpha blockers and ACE inhibitors are tied for second. Therefore, the randomization probabilities for the next wave are highest for calcium channel blockers, the best comparator, at about 30%. But even though they're tied, ACE inhibitors hazard ratio is based on about 1,000 fewer patients. So the randomization probability for ACE inhibitors is 21% versus alpha blockers at 16%. We favor the smaller of the tied arms, so it has a chance to catch up. Now we just keep stepping through approximately every 3 months, and we see the Kaplan-Meier curves maturing. The arms are looking a bit more equal, but the calcium channel blocker arm is still in the lead. At 20,000 patients, we also have a prospectively planned stopping look. The probability the best arm, calcium channel blocker still, is better than control is 82%. That's well above the 20% bound that would kick in a futility stop, but not nearly high enough to stop for success. So we update randomization probabilities and keep going. Here the randomization probability to alpha blockers briefly takes the lead. That group's hazard ratio is still just behind calcium channel blockers, but with 1,500 fewer patients, we favor its randomization probability in this update. The same trend continues 2.5 years into the study. And interestingly, at 29,000 patients, we're back to nearly even randomization across all three comparator arms. While calcium channel blockers is the best, it has the lowest hazard ratio, that arm has the most patients already. After 30,000 patients, we have another early stopping look. The probability the best arm is better than diuretic is 69%, higher than the 35% that would meet a futility stopping bound, but not nearly high enough to stop early for success. So we update randomization probabilities and keep randomizing patients. We continue, and nothing is proving to be more effective than the diuretic. Even the best arm has a hazard ratio of just 0.93. But again, we see the best two arms, calcium channel blockers and alpha blockers, have higher randomization probabilities than the ACE inhibitor. Calcium channel blockers continue to look the best. We also see this in the green Kaplan-Meier curve being lower throughout the range, and we put a plurality of patients on calcium channel blockers, the best performing arm. And the next interim, calcium channel blockers continue to look the best, and so we randomize 42% of patients to it, 33% to diuretic, 15 and 10% to the other two arms. So now we've hit the end of patient accrual 4 years into the trial. We've enrolled 42,000 patients. We see here of the comparators, there's a 74% chance calcium channel blockers are the best, followed by about a 13% chance for ACE inhibitors and alpha blockers. And in line with that, we see the plurality of patients are assigned to the best comparator, calcium channel blockers. This trial enrolled 28% of patients to the calcium channel blockers versus the 21% enrolled to that group in the actual ALLHAT trial. Now accrual is complete and we're following the patients we've enrolled. Now interim analyses only occur every 9 months because we're not updating randomization probabilities. At this analysis, we've seen more events on the alpha blockers and their event rate is now worse than diuretics. calcium channel blockers are still looking the best, and the hazard ratio is just 0.95, a small effect size, and we're getting closer to its futility bound than to the stopping for success bound. At 5.5 years, we see calcium channel blockers are still doing the best, but the hazard ratio is just 0.95, and the probability the calcium channel blocker arm is better than diuretics is just 81%. That's not nearly large enough to stop for success, and if it were less than 70%, the trial would stop for futility, meaning there's little chance that we're ever going to reach statistical significance here. We continue to track patients, and we're getting closer to a futility stopping bound. Calcium channel blockers, the best arm, has just an 83% chance of being better than diuretics. That's just slightly more than the 80% bound that would lead to a futility stop. Now, 9 months later, we see 115 more MIs or cardiac deaths on patients in the calcium channel blocker group. The hazard ratio, which is the best of the 3 comparator arms, moved to just 0.98, essentially no better than diuretics. The probability it's better than diuretics is just 75%, which is lower than the futility stopping bound of 80%, so the trial now stops for futility. At this point, the hazard ratio for ACE inhibitors and calcium channel blockers is very similar, even though calcium channel blockers were in the lead throughout most of the 7-year course of the trial. So we executed a trial with adaptive randomization, whereas ALLHAT assigned 21% of patients to each of the 3 comparators. The readapt design put 28% of patients on calcium channel blockers, 21% on alpha blockers, and just 17% on ACE inhibitors. Here we showed one simulation that stopped at 7 years. This was very representative simulation of the 500 we did using the actual ALLHAT data, and the average stopping time over those 500 simulations was 7.2 years, a 1-year savings in time versus the actual ALLHAT trial. If we compare our final estimates for hazard ratios to the results from the original ALLHAT trial, we see essentially the exact same hazard ratios and exact same confidence intervals. So even though there's quite a dramatic drift in the patient population, as described in the paper, neither the adaptive randomization nor the early stopping changed the inference we made at the end of the trial. Interestingly, we also executed all the other designs we explored in our previous clinical trials paper, and this design, even in retrospect, performed the best. This highlights the benefit of using rigorous trial simulation and study of operating characteristics to evaluate and compare many competing designs. We hope this paper and video highlights that Bayesian adaptive trials are valuable in comparative effectiveness research. They can save time, money, and resources and treat a higher proportion of patients with more effective therapies, and as shown here, produce unbiased estimates even compared to fixed trials. Thank you for viewing our video.